This lesson finishes the note sheet for 1.3 square roots. In this first example, we're taking a look at simplifying radicals. Plan B would be to break it down into its prime factors, and then because an implied index here is 2, you would take pairs of factors, and each of those will come out as a single copy in front to join with the negative. And then because we scooped up all the factors, there's nothing left underneath the radical, and so the answer would be -4. Box all answers. But that takes time. It also kind of detracts a little bit from what's actually happening. If you take a look at, say, the cubed root of 27, this index of 3 is asking us what number multiplied by itself 3 times equals 27. So that's why it's called a root. So the answer is 3. And we could see that by 3 cubed is 27. Taking the third root of something is the same as raising it to the 1/3 power. And when you raise an exponent to an exponent, you multiply. So that's 3 to the first, or just 3. But we want to do this a different way. Because we are memorizing the perfect square factors 1 to 15, so 15 squared is 225, 14 squared is 196, we'll use those to make this work faster, more efficient. So with this example, I realized that 16 is on the list of perfect squares. That's the first thing that I ask myself. And then I ask, okay, what is the base and that you square to get the 16, and that is 4. And that's the answer. This piece on the outside, realize it is -1 times the square root of 16. So it multiplies by whatever simplifies out from underneath the radical. In the next example, I'm going to look for first of all, I ask myself, is 50 on the list of perfect squares? No. So instead, I now ask, what is the largest perfect square factor of 50? And the answer is 25. And then I'm going to use the product property of radicals. And then simplifying, the square root of 25 is 5. And because 2 is not a perfect square, it stays underneath the square root. In the next example, 25 and 30 are relatively prime. So I will use the quotient property to take the square root of the numerator and the square root of the denominator, yielding 5/6. There are 2 ways to do the next example. You could realize that the indices are both implied to be square roots, or 2. So then you can multiply radicands together. 3 times 12 is 36 underneath the square root. The square root of 36 is 6. When the numbers are larger in the radicand, you might consider breaking down before multiplying. So the largest perfect square factor of 12 is 4. And once you say what the perfect square factor is, take its square root. So square root of 4 is 2. And whenever you multiply 2 identical square roots, you just get the radicand, because 3 times 3 is 9 and its square root is 3. So that's another way to get to the answer of 6. Longer in this case, but it will, before the numbers get really large in later examples, this you simplify before you simplify the radical before you multiply together, and that can help you out. In this example, we can go one of 2 ways. You could break down the largest perfect square factor of 500, which is 100. Its square root is 10. And now you divide out the like factors. You could divide because everything is multiplied together in the numerator. What I prefer is to use the quotient property, dividing before doing anything with the square root. Equaling the same thing. And once you get the hang of it, You could even just go right from the beginning and not even need to rewrite. Moving on to the next section, estimating square roots. This is just a trial and error game, but to put you in the right ballpark, you want to find two perfect square roots that sandwich the one you're trying to approximate. And then ask which one is going to be closer. So if I'm trying to approximate the number 50, that is between the perfect squares 49, or 7 squared, and 8 squared, which is 64. So when I try decimal approximations to get to approximately the square root of 50, I'm not going to try 7.9. Rather, because 50 is closer to 49, I'll probably try 7.1 first. So estimate to the nearest tenth. So let me sandwich the square root of 27 between two perfect squares. So I'll do square root of 25 and 36. Notice 25 is only 2 away from 27, and 27 is 9 away from 36. So 25 is closer. So I'm going to just kind of give this a shot. I'm going to try 5.2 squared. See how close I get to approximating 27. So it's multiplying it by itself. So that's 26.04. I'm a little off, so I'm going to jump ahead a couple. I'm going to go to 5.4. So I really missed there, so I'm going to try 5.3. I'm only trying to round to the nearest tenth. And I realized I made a mistake. This is going to be 27. Because this is 5 times 5. Because I forgot to carry the 1 here, so that'd be 26 there. So actually, I gave a little more work than needed. This is really close to the square root of 27, so then the actual answer that I would present as the approximation to the nearest tenth is the 5.2. It would be on the safe side to try 5.1 in most cases, but because I'm only 4 hundredths away from the answer, I'm pretty confident. Moving on to the next section, rationalizing the denominator. You multiply to create an exact root in the denominator. So you preserve the value of the original expression by multiplying the numerator by the same value. This technique started when we had our calculators called the slide rulers. They weren't a digital calculator and they couldn't handle radicals in the denominator. And we just kind of kept with it because it just, it does put the number in a little simpler of a form. So in this problem, I realized that it is the irrational number of square root of 2 in the denominator that's the thing that I need to simplify. So I will multiply by the square root of 2 to the numerator and denominator to create an exact root, because the square root of 2 times the square root of 2 is the square root of 4, and 4 is the perfect square I was looking for. And remember, these are both underneath radicals, so they will multiply together. because their indices are the same, so 5 and 2 make 10. And then the square root of 4 is 2. And that's the answer because this 10 is underneath the radical, this 2 is not, so they cannot divide. Next example. We want to make an exact root again. Because we're still working with square roots, it's literally just copy and paste of the irrational part of the number. But later on, when we take a look at, say, 1 over the cubed root of 4, well, that's 1 over the cubed root of 2 squared. To make an exact root here, we want an exponent of 3, so then we would just multiply by the cube root of 2 to the first. Because that will then, in the denominator, create the cube root of 2 cubed, or 8. And what number multiplied by itself 3 times equals 8? 2. So then that will be square root of 3, the cube root of 2 on 2. But for now, we're sticking with square roots, so it's much simpler than that. But just don't get into a wrong generalization of how these are actually simplifying. So right now, I just take the irrational part of the square root of 5. The 3 is fine. It is a rational number. That can be in the denominator. So we got 5, square root of 5, all over. Well, square root of 5 times square root of 5, square root of 25, which is just 5, so 3 times 5. The 5 simplify for a final answer of square root of 5 on 3. Don't say root 5 on 3. It is the square root of 5 on 3 to distinguish it from, say, the cube root of 5 on 3. In the next example, why not use the quotient property? So now it's square root of 1 over the square root of 4, which is just 1/2. Simplifying first is always the way to go. Looking at the last part of the lesson, addition and subtraction of radicals, you have to have like indices and radicands. In order to add or subtract radicals. If you don't have that, but like in this second example, you could simplify and achieve like radicands and like indices, then you could go ahead and add or subtract. Looking at the first example, we already have set up like indices and like radicands, so then we just operate on coefficients. Much as if x equals the square root of 3, we could treat this problem like 9x plus 7x, which is equal to 9 plus 7, or 16 copies of x are present. It does not square the x. We are not taking x times x. So that's why we're only working with the coefficients, and here we get 16 times the square root of 3. And the last example, I need to simplify first. The largest perfect square factor of 20 is 4, and its square root is 2. So that will multiply on the outside. And then the square root of 5 stays underneath. So I multiply 3 and 6 to get negative 6 as the coefficient of that second square root of 5. So now the problem becomes 8 of these square roots of 5 minus 6 of these square roots of 5 for a total of 2 square root of 5. Box your answers.